A lot of repetition for you. Yeah, I'll try to do 50 minutes and then a break and then 50 minutes. And I would like to start with motivation, a bit the big picture of what we are speaking about. And maybe the first question I want to answer is what is the early universe? So if this refers to a precise time threshold, and the answer is yes. So this is the big picture. So in general, any history of the universe begins with something we don't know. But what we know is that the universe has always been expanding and cooling down. And when I say always, I mean how far we can count back in time. So if we put our ignorance at 0 seconds, so this is a timeline. So always means, I think it's 100 petaseconds. So we are here. And we said that the temperature was increasing as we go back in time. So this is the temperature line. And I measure temperature in electron volt. So my units are H is 1. And the early universe starts as soon as the first atoms were formed. So this is about 10 to the 10 seconds and 1 electron volt. So this is a very special moment because just before the temperature was high enough that the interactions between electrons and photons were very efficient. And the photons could dislodge the electrons, so they could not bind to the nuclei. But this also means that the photons were interacting a lot, and light could not propagate through space and time. So the light that was emitted as the first atoms were formed is the oldest light we can observe, and is called the cosmic microwave background. So I don't need to break down the acronym for you, I guess. Yes, and most of what we have predicted for the early universe, that I said it starts here. Within the standard model, at least, was to explain the feature of the cosmic microwave background that we observe thanks to electromagnetic radiation.
So what's the temperature now in electron volt?
Ah, yeah, 10 to the minus 3, so milli. Sorry, thanks. And yeah, okay, and for decades, we thought we don't have any other direct probes of the early universe until a few years ago humans measured gravitational waves for the first time. And this is the big revolution in the early universe community, because gravitational interactions become efficient at a much earlier time. So we expect something like this. And to see when this happens, we can just take Einstein equations of general relativity and investigate this gravitational constant. This is something like this in SI unit. I think it's kilo. Check. And now I want to go to these units. So, okay, this is I just care about orders of magnitude now. And then I have something which is probably like this. So this is kilo meter cubed as 2 over h bar c. And then I need some 1 over kilo squared. And this is, I think, 10 to the 35 electron volts minus 2. Yes, this is kilo and h bar c. So the overall orders of magnitude, if we write this constant at h bar c over a mass squared, then this mass has the order of magnitude of 10 to the 28 electron volt. And so this is what I put here. And it is, so 10 to the 28. It corresponds to a time scale, which is called Planck time scale, which is minus 44. So in principle, any the gravitational wave that has been sourced at any time later than that could propagate freely to us. But on the other hand, those signals are diluted by the entire expansion that happened from that early moment to today, and therefore they are also they have the same characteristic of the cosmic microwave background, that they might be detected as a noise in our interferometers, and this is why we call it like gravitational wave background. So we hope to detect it, and this will be a hard exercise to extract the signals. And now maybe let me, so I was writing a bit bigger, but let me sketch some sources that we would like to probe. Hey, with gravitational waves, and I start with sources within the standard model. So those are standard sources. First of all, we have some phase transitions. For example, so I'm running up. Okay. The QCD phase transition, so where free quarks and gauge bosons confined into hadrons. And this is and then we also have the electroweak symmetry breaking. Okay, I don't have a better sketch than this. And this is about 10 to the minus 10. And so this is one phase transitions. And apart from these isolated moments of non-equilibrium physics, we expect that most of the time standard model fields were in equilibrium with each other. But also a thermal plasma in equilibrium can emit gravitational waves. So this is another standard source. And finally, not really within particle physics, but cosmology, we also have their fairly accepted model, which is inflation. And it's expected to happen. No, it's larger than 10 to the 6. Yeah. Like if you ask nowadays to lattice people, they say 200 or so, but yeah. Yes. So it's not a sharp line for me here. But I think this is undergoing research. Yeah, and inflation, I just don't know the temperature. And inflation is a model that predicts short but brutal expansion of our universe. And it happens probably at about 1 quectosecond. So this is another, like, I say standard because it's well studied.
What do you mean by standard sources from the thermoplasma?
Yeah, it's a plasma where we consider all standard model fields to be in thermal equilibrium with each other. So I mean standard because I just have standard model here.
Do you mean like standard gravitational wave source? Or standard?
Oh, yes, standard for me means like standard model physics, not PSM. And plus accepted Cosmo model. Yeah. Inflation is, if you want, beyond standard model, because we don't need it to explain anything that we observe at CMB or later. Or like we need it for CMB, but not anything later. But we don't yet have direct probes of inflation, so it is why standard, yeah.
And the inflaton is beyond the standard model?
Yes, the inflaton.
How thermal plasma can create a background of gravitational wave? You're going to tell us about?
Yes. So, like, this is like the plan of this course. Because, okay, so those are the most studied sources, I think, that would come into the gravitational wave background. And not only, but the methods to compute the gravitational wave spectrum in these 3 cases are different. So even if you are maybe working on a beyond the standard model scenario, you might land in the same shape of problem. So it's like to give you the models, the methods I know to solve for the gravitational wave spectrum. And maybe I just cite some exotic, which means like beyond the standard model and different cosmic history, so from inflation. And for example, so the most famous ones are primordial black holes. And then we have cosmic strings. And then we have something a bit special that are higher order perturbations. And I put that in a parenthesis because in principle this is not really exotic. So it doesn't require anything beyond the standard model, but in order for these signals to be anything we can observe, we need a quite different cosmic history. So you don't need it in principle, but if you want something observable, you need to modify the history, and this is what is usually done in all papers you might see. So,
yeah. Second order scalar perturbation has been known since long time.
Yes, exactly. But they are very suppressed if you don't modify cosmic history. So I put them in exotic. And yeah, and this is not, we won't cover it probably, it depends. But maybe you are also more expert than me about this, so maybe just a little bit on my background. I did my thesis with an expert in thermal field theory, so meaning quantum fields at high temperature. So our range of the place where we find ourselves at home are really like these phase transitions and thermal plasma, because there you really have to deal with quantum fields or out of equilibrium physics mostly, and yeah. Quantum. No, I mean, I also not really an expert. So I can say you something, but it won't be anything special that you don't find in the introduction of any other presentation. So yeah, I think we can chat about it. So, but I don't think I have anything to teach anybody. Okay, so this is a bit the plan, and I think this will be mostly on Thursday, and this will be mostly on Tuesday. And today, I would first introduce all the basics formula I need that I will then apply for all cases. And yeah, and basically the question that we ask us, so, okay, but what are exactly gravitational waves and how are they sourced? Okay, and I like sharp answers, so I will already give answers and then we go through it. So what are gravitational waves? The fast answer is our perturbations of how we measure space distances. But yeah, I guess you know most of it, but just to have that we are on the same page, I will go through it. And how are they sourced? Via anisotropies. Tropies in the matter content of our universe. Okay. Good. So this is the plan. I guess. Let me check the time. Good. Let's see if I. It's looking a bit dangerous there. Okay. So I think we can start with looking deeper into perturbations of space-time. So we know from observation that on large scale our universe is homogeneous and isotropic. And in the early universe, we said that all the Sono model fields were interacting almost close to equilibrium. Therefore, we don't have clumps. So this is a very good approximation. And we can also assume that all the perturbations around this homogeneous and background universe are small. And therefore, we can expand the metric to first order. So, and I use a bar usually for background quantities. And then we have some. So this metric depends only on time. And then we have perturbations that depend on time and space. Maybe I want for the moment to be generic, so this is x0 for me. And we neglect all high order terms. Okay, and so this is like in general what we do, but when I should also say something about the background universe, because whenever I will take derivatives, I will refer to this universe. So I write the line element. It's called, in general, the Friedman-Limit-Robertson-Walker metric. And like the physical choice of coordinates is with time direction, and then a scale factor that describes the expansion of the universe. And I'm a bit sloppy, so I assume that the universe is spatially flat. But this is also an observational fact that it's almost true. Okay, so this is a physical coordinate system, but most of the time I will use other coordinates that are conformal coordinates. So this is the only thing that changes the time direction. This is conformal time. Theta times A is defined as the cosmic physical time. And if I use these coordinates, so it's nice because you see this is mostly Minkowski metric. So I can also use it to describe the perturbations. I can write the background quantity like the Minkowski metric. And I call h mu nu the first order perturbations, and then we have high orders. So this is conformal. And it's called conformal because, yeah, this metric is related to Minkowski metric via conformal transformation. Okay, I set these derivatives, so let me set the notation. So derivatives with respect to cosmic time, I use a dot, while derivatives with respect to conformal time, I use a prime. And then if we want to express, so say how fast does the universe expand, in general we use the Hubble rates, which in this word is A dot over A, and in this word I use a curly H, and this is a definition, is A prime over A. Okay, I think this is it for the notation. So we want to study perturbations in space distances, so this would be the ij component of this, which is not really a tensor because it transforms under coordinate transformation in not like a tensor. But sometimes I will say tensor. In any case, in principle it has at least 10 components because it's symmetric. But we are not interested in all of them. We want perturbations in space distances, so what is here. And also here, so we have some perturbations that I called D, diagonal, that are related to, that can be reabsorbed in perturbations of the scale factor. So these are less interesting. But we want like the true perturbations, so the ones that are traceless. So I put a T for traceless. And so Hij in principle has, okay, this is 3 times 3 minus 3 minus 1, so 5 independent components. But some of them are redundant under coordinate transformations. And under, so I take a small coordinate transformation when I shift by a vector, and I can write this. So it has, of course, a time shift, and then I can shift like perpendicular to the direction, to x, or in the same direction of x. So this means that I can write this longitudinal part as a gradient of a scalar potential. So if, okay, we can decompose xi like this, and then we decompose also our Hij t, depending on how it transforms under this transformation. So I write Hij t, and now notation is starting being a bit messy. I have it Ts, Tv, and Tt. And basically, so we are doing a similar decomposition. So those are perturbations along the propagation. So therefore, we have 1 degree of freedom. Those are perturbation like one along the direction of propagation and one transversal. So we have in total 2 degrees of freedom, because we can either have a perturbation in this plane or in this plane. I don't know if I can render. Yeah. So 2. And then we have fully transversal perturbations. It's even harder to draw, but it's either we have this type of perturbations or this type of perturbations. Okay, and if we now apply coordinate transformations, we have Hij(s), which can be written again as a gradient of some scalar potential, and the scalar potential just transform with the longitudinal transformation. Then we have the vector part, is called, which is something like, it's written as the gradient of some vector potential. Which must be transversal and transforms just in the perpendicular direction. And finally, we have the transverse and traceless components. Okay, those I cannot decompose in terms of potentials, but we know that they must be fully transversal. So if I take derivatives, contract, they give me 0, and they do not transform under coordinate transformation, which is a very nice thing. Good, so we see that in principle, if we fix a gauge, so to say, we can eliminate the other components, and the true perturbations of space distances are the ones that are fully transversal to the direction of propagation. And these are the ones that we want to study. And when I say want to study, means we want to know how they evolve. And this is governed by Einstein equation of relativity, of general relativity. Which is here. So if we now evaluate Einstein equation for the metric perturbations, in principle we obtain a quite complicated object. And let's look only at the ij component and delta because it's the first order in linear perturbations. And okay, so I should also not forget that, so this is h mu nu, but at the end we want, so we are evaluating Einstein equation for h mu nu times a squared. And I won't write down everything, but you might see the pattern that we have all these decompositions. In principle, like just looking at the tensor structure, I could have, I could have first of all a scalar, simply multiplying some delta ij. Otherwise, I could have some delta I scalar, delta j scalar, and otherwise delta I, delta j scalar. This is all we can do with scalars. Then we can start working with vectors. We could have delta I vector j plus delta j vector I. But we have learned that they all transform on the coordinate transformation. And finally, we have what we want is what we call the tensor component, which will look like this. I'm using conformal coordinates. So the operator that acts on our TTIJ object really looks like a wave operator. And okay, right here, it does. So this term does not transform under coordinate transformation. So wave looking. So cool, we have a wave operator acting of our gauge independent, I wrote invariant, it's not really correct. Acting on our gauge independent object, so I can maybe call it now object. And therefore we see that if we now would apply the same decomposition on the right-hand side, this very term must be equal to the same piece of gauge independent term we will have on the right-hand side. So this must be equal some delta, so APG, and then delta T IJ, traceless, and transverse. But okay, so I mean just the linear perturbations of the energy momentum tensor, traceless and transverse. And if I think about what are those perturbations, so it's exactly the same picture as before. But okay, I just take this part. On the diagonal, we will have perturbations of the pressure if we are thinking at a perfect fluid. Otherwise, we might have some bulk viscosity also, but I mean, this can be parameterized in here. And then everything that is not there is what we want to have in the equation. So those are all the components that are off diagonals in space. And this is really what we usually call anisotropies. Because if the universe is isotropic, we don't have anything there. So those are anisotropies. And okay, now I would like to give some better names. So I just simplify the notation. I call Hij, what so far we had Hij tt, and big pi ij, just because I don't want to carry all these indices around. And with this notation, then the gravitational wave equation we obtain is okay, so this will the gravitational wave equation that is the starting point for all the calculations today and in the next days. I just check the time. Okay. I have 5 minutes, maybe.
We are easy with time.
Okay. Yeah, but maybe it's good to have a break at some point. Okay. So, okay. Yeah, I told you all this story about coordinate transformations just to motivate why we arrived to this equation that is often just stated, and I think it's important that it's important to realize that we have some gauge invariance here, because often when one looks at some exotic sources like second-order scalar-induced gravitational waves, we really have some gauge issues there. So this is like a caveat. Your gravitational wave equation must always be gauge invariant. And if it's not, there is something wrong going on. And yeah, so but we won't need it maybe until the end. Okay, and now like maybe the next question we should ask ourselves is, okay, what do we measure? Can we measure Hij? And not. We cannot measure Hij, but we can rather observe its power spectrum. So this is what I would like to derive now and maybe motivate it. Okay, so if we are in a local Minkowski frame, then which is what we can use mostly for observations today, then the energy density, or the energy which is associated with Hij, or with gravitational waves, the energy and so this is really an energy, and maybe I put some GV here, And I write M just to make clear I'm using a local Minkowskian frame. And so this is quite a very intuitive formula. I have some normalization which comes from the action, and then simply like the average over space coordinates, and yeah, I mean there is quite a lot of assumptions going here, but mostly this is the easiest expression we can write, and it applies in most cases. So when we want to extract an energy density, we can write this really as an average, where we divide by the volume of Hij, which is taking at the same point, but meaning also at the very same time. So this is an equal time correlator. And so I was writing here like the derivatives with respect to physical time, because this is what we so it's the coordinates we use for measurements today. And in fact, we don't directly measure the energy density of gravitational waves, but rather like the fraction of this energy density with respect to the total energy which is stored in, okay, we measured it today. The total energy which is stored in relativistic degrees of freedom, and we have an expression for that. And H0 is the Hubble rates today, which is parameterized in terms of a number we are not agreeing on. And it's not really this fraction we measure, but like its dependence on the frequency on a logarithmic scale. So this is the gravitational wave spectrum is our observable, but mostly you will see we extract omega GVH squared because we don't know H. And in terms, not really on the frequency K, but rather on the frequency today, which is, of course, like the universe has expanded, so physical momenta scale correspondingly. And like today, the physical momentum is given by, is scaled by the scale factor today. And for most applications we study here, we are interested in a specific frequency range, which is the one at which LISA will be operating. And LISA is a space interferometer that will be launched
10 Hz?
if you are very optimistic. No? Yeah.
10 to minus 1, no?
Okay, die.
You really make it 10 Hz?
Well, like the tail. No?
Which sources you expect to be so high there?
Oh, all sources. I mean, mostly we will have peaks.
Okay, then you tell me later.
Yeah.
If you can justify, I accept it.
Yeah. We will mostly have peaks at 100 Hz, I would say, for thermal plasma.
Okay. I'm eager to learn about it.
Yeah, but in any case, too weak to be observed by LISA. Yeah, so LISA is designed in particular to be sensitive to a gravitational wave background.
No, but I mean, the 10 Hz LIGO is, I mean, not 10, 50 Hz LIGO is much more sensitive than LISA. So if you see LIGO things at 10 Hz.
Yeah, but LIGO cannot extract the background, right? Or is it possible?
Depends how many you have. I mean, LIGO, there will be, in 10 years, we'll have, I mean,
Yeah, okay.
next one, we'll have maybe, I don't know, 5, 6 detectors.
Okay. Yeah, then maybe I should look into, because
We can discuss later.
yeah. Oh, okay, so usually LISA is very popular in the early universe community because it has been designed like with the idea of extracting also the gravitational wave background.
The milliards correspond to the QCD, no?
Yes. Yeah. But also I think like the fact that it has this shape like with the 3 arms, so it should make data analysis easier to extract and
Only one detector is the best.
yeah.
Terrestrial detector will be many in 10 years. By the
Yeah.
time LISA will work, probably
Okay. So it's good to. I mean, I'm here to learn more about all this observation. So if we speak just about LISA, more or less we are in this frequency range, and then the sensitivity of LISA is something. So I should, I think 10 to the minus 13, but maybe you know better than me. Yeah. Yes, 13. So. Okay, so this is more or less so like the magic numbers we will always look at. If we compute power spectra with a peak amplitude which is lower, so smaller than these numbers, it means we probably won't be able to see it, maybe than with LIGO or so in the future. And this is mostly the case for the sources I will present to you, so sadly. But in any case, I think there is a lot to learn there. Okay.
Anyway, we know very little about the primordial universe, so something exotic might have happened.
Yeah, this is true. This is true. But it's also true that like there are many stochastic signals that come from late universe that might obstruct the procedure of extracting early universe signals. So I don't know. Okay, I have another observational constraints, but maybe we can take a small break here and go on later.
Also, usually a blue spectrum is hard to obtain astrophysically.
Yes, okay.
If you see a blue spectrum, then it's not a proof, but it's more likely to be primordial.
Yeah, exactly. So I would say if we have special spectral shape, I mean this is what we are always asking for, then it will be a smoking gun of early universe physics.
Will you talk about possible interpretation of the PTA excess?
I think at the end, because so the standard sources in any case do not enter the PTA range, and then all the others became quite famous for PTA predictions. So cosmic strings maybe ruled out, but primordial black holes are candidates, and scalar induced mostly.
I mean, phase transition, I mean, if you just shift the energy, no? You cannot?
No.
Why not?
I'm very pessimistic about phase transitions because the first the first calculations were done in a very enthusiastic fashion, and they were like heroic, I would say. But now we understand the physics much better, and redoing all this entire calculation first of all, we can correct the amplitude by at least 5 orders of magnitude. And we see that we have orders of magnitude uncertainties from the theoretical point of view that have 10 orders of magnitude. So, yeah.
Which kind of resolution are you talking about?
Yeah, standard model, like the easiest beyond the standard model version. So like just adding a scalar field to have a first order electroweak phase transition also. But yeah, or being a bit agnostic, like, and just assuming like, that you have a scalar field added. Yeah.
Next to the corner beyond the standard.
Yes, exactly. Yeah. So I think those are the most interesting signals to study because they contain so much non-trivial physics. But I'm quite pessimistic about their observational signatures. Yeah.
But you will talk about phase transition.
Yes. Yeah. Yeah. I think it's my favorite topic. But yeah. So I will do, I don't know, 10, 15 minutes or
No,
time.
5 minutes.
5 minutes? I don't know. If you want.
I do need a break. So I finish by 5.
Okay. Okay, so we have another observational constraint that is often used, and this is a bit of different nature. It doesn't come directly from gravitational wave observation, but is rather like indirect. So here I have 10 to the 3 missing. So at the moment where the first nuclei or light nuclei were born, we also have more or less neutrino decoupling. And we can use these very special moments to constrain gravitational waves because, okay, so this formation of the first nuclei and neutrino decoupling happens in a radiation-dominated universe. And yeah, I have the formula here. And if the energy density is mostly given by relativistic particles, then so the expansion rate of the universe is given by this formula here. So just not with a 0, but at another time. And this means that so when we measure the abundances of the light particles that have formed here, we can somehow we can constrain the expansion of the universe. So this is a quite complicated relation, so I cannot map in an easy way. But you see that if we have so this time here will have an so how long is this time distance will have an impact on how what are the abundances of the different light elements we measured at the CMB. And therefore we can say how fast has the universe expanded. And saying how fast the universe has expanded, we can put constraints on this left-hand side. So, of course, relativistic particles, they are photons, no doubt about that. And then, since neutrino decoupled at the same time, they also contribute to this energy density. And in general, we have 3 of them, but we don't write 3, we write n effective. So this is the effective number of neutrino species, and then we might have other contributions. So this might not be quite 3 because of some propagation corrections, but we might also have some other particles that contribute to this relativistic energy density. And it is maybe a bit unfortunate, but conventionally, adding more relativistic species is absorbed in what we called delta NF. So, okay, this is maybe, this is like a parenthesis, but I don't want to start a new blackboard. So, delta NF is basically NF minus 3, if you want. So, I often do the joke because I'm based in Bern and there are so many G minus 2 people. So I say in cosmology we have N minus 3. So, and you see that if we have gravitational waves emitted, those are also relativistic degrees of freedom, and therefore they must be included here. And the way they are included is precisely not directly the gravitational wave energy density, but again a ratio with respect to neutrino energy density. So this is like another constraint we can put. And since this is a constraint on like the total, so like this fraction of the energy density, it is not the power spectrum. So if we compute the power spectrum of gravitational waves, we can obtain then the constraint by integrating over all frequencies and renormalizing that. So it's like an observational constraint we get for free once we have already the power spectrum. Okay, so these are
But this delta effect you calculated at the time of the emission of the gravitational waves, or just as some delay or some conventional?
Yes, you should, like in principle, you should integrate also over time. Like, but it depends. So, like, if you're interested, if you have a source at some point in your cosmic history, it emits gravitational waves. They will enter an effective here. By the way, this moment is called Big Bang nucleosynthesis. Yeah. The gravitational waves emitted here will enter the prediction of Big Bang nucleosynthesis, but like you just need to know how much of them are sourced. So if you have a long-lasting source, you have to integrate over the full duration, and then they will just free propagate. But of course, so this is like one contribution. If you have many sources, that they would all sum up to this number. So if you get sharp, that number is not good. It should be below. It's an upper bound. Yes. So in this sense, is not. Yeah, it is a useful constraint because you can always compute it, but it is not a stringent constraint at all. It's usually always a very upper bound you will never reach, but it's good to rule out models that are far not in the good direction. Yeah, if you overproduce gravitational waves, you will immediately see with an effective. Okay, so I think that's it, and now I'm already here, so I will erase this, and we start deriving some formulae for the power spectrum. Okay, so this is maybe like the true title of this course, how to compute the power spectrum. And those are also generic formulae. So, and afterwards then we will apply, or we will compute concrete examples. Okay, the first thing to mention here is that, okay, here we have a second order differential equation, which is non-homogeneous in most cases. And okay, we have space derivatives and time derivatives, so maybe it's a good idea to transform to Fourier space, because at least we get rid of this nabla here. And okay, the result is, so it's easy to guess. Momentum, space, And maybe I should also clarify how I'm doing this transformation, because like it is non-trivial in cosmology. You should always think which metric you are using, and if you are transforming only space or also space and time. So here, most of the time, I'm transforming only space. So I'm in a co-moving frame. And I use it's co-moving because I'm using conformal time so I'm locally Minkowskian. And then the expansion in Fourier mode, yes, is done in this way. And then here we simply have, I don't put any hats or tilde or whatever, I have a different argument. And my convention is here is no minus. So this is the Fourier expansion. And now that we are working in Fourier space, we can recall that like this Hij was our Hij transverse and traceless. So it had two components, so 2 degrees of freedom. So also its Fourier transform has only 2 degrees of freedom, meaning that this is in fact a stupid basis to work with, because we have too many indices. And a better choice would be an helicity basis. So helicity means that we can write Hij. So now in Fourier space, in this basis, and we remember we had 2 possible configurations. One is like this, and the other one like that. So, but just 2 helicities, and we have an helicity tensor, which depends only on the momentum, and then we have the coefficient that depends on both time and momentum. So this is quite a nice decomposition, because if we insert this back, the helicity tensor does not depend on time, so we can put it on the left. And moreover, we have some sum rules. So they can be derived simply, so like by construction of those helicity tensors. They must be orthogonal to each other and normalized to form a basis. And therefore, like if we are contracting, let me write this correctly. If we are contracting 2 different helicities, but we contract the indices, this is lambda, lambda prime, and we sum over lambda and lambda prime, then we get like a delta. So this just means that this is a basis and is orthonormal. But we can use this because, like, I'm not already writing everything, but here at some point we want to compute some 2-point functions with contracted indices. So an object of interest will be precisely when we have 2 Hij. So one is given by epsilon ij lambda, and if we are taking them at the same momentum, okay, now I'm writing, then I have h lambda dk h lambda prime tau k. I will precisely recover this delta lambda lambda prime. and this object is then just a sum over 1 lambda. And okay, now we are in Fourier space, so I should complex conjugate. So okay, this is already quite useful. We simplify our notation a lot. And yeah, I'm quite lazy, so then I will also drop this lambda, because if we insert like the decomposition in terms of helicity, I said the helicity tensor will come out of the equation, and you see that both helicity components will obey the very same equation. So we have basically 2 copies of the same solution. And it's not really important which copying we are looking at. Of course, like there are then applications where it's very interesting to have more gravitational waves of one helicity than the other, so one can restore this back, but to derive most equations, we don't need to specify which helicity we are looking at. Okay. So what we now need to do is to relate this average over space coordinates with an average in momentum space, because at the end of the day we want to take this derivative and extract the power spectrum. And so what we have to do is transform these guys to momentum space. And first of all, maybe I can erase there, and well, no. First of all, we have this, which is written in terms of physical time. Okay, if we transform to conformal time, we just get a factor 1 over a squared. It's getting a bit messy. Okay. So I will now just remember that I have an a squared to add in the gravitational wave spectrum and compute this. So this is the reminder of what we are aiming to. Okay, so let's Fourier transform this guy here. So yeah, it's again an equal time correlator. And it's a special average. So if I now write explicitly this average, okay, first of all, I should divide by the volume. So if you are doing observational physics, this is maybe not the infinite volume, but we are computing the theoretical prediction, so this is it. And then we have this. Okay, so nothing special. I use this Fourier decomposition. And so finally I have two different momenta because I have two different objects here. I also have still this integration of a spatial coordinates. And then let's put all the phases together. So I have minus I, they have the same spatial coordinate, so it's x. And then I have p minus q, just because randomly I've chosen q to be the momentum of the second guy. And yeah, that's it. Now I have our objects here. This is p, and this is q, I said. Okay. I mean, the derivative acts only here because here we don't have dependence on time. This is a delta function in 3 dimensions. With 2 pi cubed. So we can use it to evaluate one of the integral over momentum. And we are left with p, say. And then we have those that are evaluated both at p now. Ta-da! But here we have something that really looks like this. So we have time derivatives on top of that, but they do not act on the Licity tensor, so I can apply the sum rule and simplify this object. So we said that this is sum over Licity, and then I am left with h lambda prime. So p. Oh, I forgot something. So this was complex conjugates. This was also complex conjugates. So here I have this. Okay. And yeah, this was what I have. So now we keep this volume average there. We have this nice object. We can put it just on front. And then we also have this spatial integration. It's usually a good idea to use spherical coordinates, so we might have some radial integral. And then we have, I just denote like the solid angle integral like this. And the 2 pi cubed comes in here. And just yeah. Okay, we are almost there. Okay, here we have k. In the integral I used p, but we see already this can be expressed as a integral over a logarithmic interval. I just have ln p and then a p cubed. So we can already identify the power spectrum. And this is not yet omega GW, because I need prefactors and so on, but I call it the power spectrum of H. And we identify, okay, so no, I just write it down. We identify this as the limit L to infinity. And then I have some over elicities. I take this by the normalization, everything here, and also this P. I want to take it in the power spectrum. And finally, this solid angle integral. Yeah, so this is, if we define this object like this, then we can already write our two-point function in a shape that looks very good. Wait, because this is then pH, tau, and k. So as a check, our result depends only on the modulo of the momentum. This is fine, and all the prefactors are away. Yeah. So we are already able to take this derivative with respect to the logarithmic interval of the frequency, meaning that the result will contain only the power spectrum. And in most cases, okay, so this is, I think, a formula which is quite intuitive, because we started with an average over a coordinate space, and we ended with an average in momentum space. But in most cases, if we are in the early universe, we don't really know how to take averages over momentum space. If our sources are stochastic, meaning that the gravitational waves are sourced by some random processes that might happen, like they don't have a precise dependence on the momentum, but they rather have a well-defined correlation, and that behaves like a momentum conservation. And in these cases, so if the gravitational waves are sourced randomly, what we can assume is that in this infinite volume we are averaging over, many different configurations could have occurred, and therefore we can replace this average over momenta by a stochastic correlator. Place volume average. So, and the formula is then a bit nicer, I think. What is basically done is that we say, okay, so this is per se a power spectrum that does not depend on the direction. So we carry out the angular integration, and we are left with just this, and I should not forget the helicity. And finally, yeah. Okay. So I've cancelled. So this is. I'm telling some subtleties, but I think it's important to be careful in these calculations. I've cancelled this 1 over L cubed, because in principle, if we are in a stochastic approach, here we would have p minus p delta function, but this is L cubed, so cancelled my L, I don't need the limit anymore. Okay, so we have a final formula for the gravitational wave spectrum, here. So all in all, what we have found is that so after taking the derivative, we are left just with ph, tau and k. Okay, so in general, this should be taken at the time today. And then in the denominator, we had, okay, here I have twice this because of helicity. They have exactly the same spectrum. Here we had 3 by j. Then I have a squared because of transform it to conformal time. And then we have this critical row, which was h0. This is then also 0, h by j. So finally, we have
Sorry, we've been using h prime all the time, so it's derived in conformal time all the time.
yes,
Okay.
it's derived in conformal time. But the difference is just because for most sources it's easier to have conformal time. And the difference is just, yeah, by
No,
this.
my question was
Yeah.
so it wouldn't be easier to trade derivatives with powers of p's?
With powers of p's.
Yeah, you have your p there anyway. So you have p and derivative with respect to time. You have the two.
Yes.
Why not adding power of trading derivative with respect to time for p's? No, you don't want to do that. Is there a reason why you don't want to do that?
Well,
Because you want to eventually go beyond the horizon with this?
yes,
Okay.
I mostly go. Yeah. Wait. Okay, you can do it most of the
Only with
times.
horizon, of course,
Yeah.
if you want to go.
Yeah. Like for the generic case, I'll keep the time derivative, but it is true that we never need to take the time derivative really of this function. So what is mostly done is that
So this is actually p of h prime, not p of
this is actually p of h prime. And then there are different ways to carry out this prime. One is like, yeah, converting the time derivative, or yeah, carrying the time derivative, and you get some powers of p. Or what is a method I will often use is that, in fact, like we have sources that are finite in time. So we have ph prime will be like the ph taken at the end of sourcing time times some easier, so it's not easy. It's a very complicated function in real time, in fact, which also depend like.
Okay,
No, but like, yeah.
you're making a more generic
Yeah.
picture.
Yeah, so in general then the dependence on time is encoded in how the wave propagates to us, because this prime here is a derivative taken with respect to tau 0 to t0. No, to time today.
Okay.
So it in fact only acts here. So only in the propagation period, not on the source. So yeah, maybe this is something to specify. So this is a derivative with respect to tau 0. Okay, so yeah, this is the, I would say the final formula, and to make it clear, because there is maybe a bit messy, I also write down again the formula for the power spectrum in the two pictures. So either we have, yeah, I now just use a 2 for the helicity. We have this, and then yeah, and in this case, so when I write this decomposition, what we are decomposing is really H, so which can be a functional of itself, almost like, I don't know, I write like some x that propagates H from initial end of sourcing time tau star to today, and depends of course also on k, and then I have H at tau star and k. So then these derivatives only act on x here, and I can really write this like this transfer function depending on tau star tau 0 k times ph tau star k, and this is in general, well, here I have absorbed all the prefactors. And then is the tau 0 and this mostly this. Okay. Yeah. The good thing, so this is like the very same decomposition that is usually done for scalar perturbations at the CMB, and there computing this transfer function, it's a mess. And the good thing is that for gravitational waves this is not the case because they do not interact almost. So what we need to know is, well, the only difficult part of it is knowing for each momentum when is the correct time to start propagating freely. After you know that, this is it. Okay, and yeah, we will mostly use this picture here, but yeah, just recall that it comes from an average over all possible directions of the gravitational wave propagation. Okay, I think this was more or less what I prepared for the first lecture, but I'm happy to take questions or, yeah.
So you set up the stage?
Yes.
The physics is yet to come?
Yes, exactly. But the physics is done quite easily once we have all these equations. Yeah.
I'm not sure if I follow completely this point where you have, like, you can take out the time derivative.
Yeah, so the idea is really that if we look, I erased the, no, maybe not, yeah. If we look at the gravitational wave equation, that was yeah, I just put some. So the gravitational wave equation is like this. And this means, okay, as long as your source is active, what you do is that you solve the equation using Green function most of the time. But then at some point, if, yeah, like in the early universe, the sources do not last forever. So you have, for each momentum k, you have a moment where the source is negligible at some point. And what you do is that then you solve the vacuum, so the homogeneous equation. And for this equation, what you really need to know is how do the momentum compares with the expansion of the universe. And if you're looking at small momenta, I mean, h is a time-dependent quantity, so depending on which moment in time you're looking at, this comparison is different. But when h is like much larger than k, and this is like, it's easier to see in physical coordinates, so this is h is much larger than the physical momentum. So, and this, if we rephrase it again in easier terms, means that gravitational, so the expansion of the universe happens, is more efficient than any microphysics phenomena you can have. So the leading order dynamics is the dilution, is not particle physics. And in this case, okay, if you neglect this term, then you see that whatever initial value this object takes, it will remain almost there. It will just be diluted. So this is the idea of this decomposition. The evolution of your gravitational waves is almost trivial, starting at some point in the history. So, yeah.
So this is what you find in books referred to as inside or outside the horizon?
Yes. Yes. Yeah, well, horizon means Hubble horizon, so meaning being larger or smaller of h.
It's not GR horizon?
Yes.
It's just h to the minus 1?
Yes. Yeah. Exactly. Yeah. So, okay, this is the game we play most of the time, at least for inflation. And but then, like, the non-trivial part to compute is the power spectrum from the source. Yeah, and of course, like, always asking, okay, when does this happen? When can I start at trivial propagation? Yeah, this is really a momentum-dependent question, and depends also, like, on the source you have on the right-hand side. When is a good moment to neglect it? So in general, you have a lot of physics going on because you have many different physical scales that you have to compare, and this is maybe the feature of gravitational wave physics we have less under control for the early universe physics, because we also don't have so much under control all these physical scales. Okay.
Maybe just one more.
Yeah.
When you wrote the power of gravitational waves, you normalize by the energy density of radiation illumination.
Yes.
Is this like you assuming that the gravitational waves emission were at radiation illumination, or
No, I think, okay, maybe like Ricardo knows better than me about this. I think this is rather like a normalization with respect to the energy density, the full energy density you measure in like from radiations or from relativistic particles.
No, but this is usually normalized with respect to the critical density.
Yes.
Okay. So the whole of the energy.
Yeah.
Of course, it's.
But it is. I mean, this equation is true. That EC often is called like critical. This equation is true only for radiation domination. Otherwise, you would have pressure.
That's the definition, H squared. That's the
Yes.
definition of critical.
Yes, but I mean, this is the equation for a radiation-dominated universe, right? Huh?
No, that's the definition.
Yeah, but it comes from the Friedman equation for a radiation-dominated universe.
And the Friedman equation is the 0-0 Einstein equation.
Yes.
Whatever rho.
Yeah, and it is.
If you put all of the rho, that holds. That's the 0-0 Einstein
No.
equation.
Ah. Okay. Yes. Yeah. It's true. Yeah.
This is it. I mean, what's the point? No, is that once you assume they're produced in the primordial universe, so as z way larger than 1,000. So their ratio to the critical density stays the same. Then when you go to matter domination, the ratio to the critical density start decreasing because they are shift as 8 to minus 4, whereas the critical density. So I mean, that omega is usually constant up to the matter domination, and then you have an extra one plus z in the denominator. So during radiation domination, if you put there one or the other, radiation or total matter is the same. But then you have to be careful with it.
Okay.
Let's thank Simona.
Thank you.